Hello, my name is Nicolas Levy, and I am going to talk about EnsNano, the software that I am developing as part of my PhD project supervised by Nicolas Chabanel. Here is an overview of the currently available tools for designing DNA nanostructures. These softwares can be divided into 4 categories. The tools that provide a 2D interface and an abstract representation of the design, those that provide a 3D editable view of the design, the tools that handle automatically certain parts of the design process, and the softwares that provide thermodynamic analysis and molecular dynamic simulations. All these features are helpful for a designer, but are currently provided in different softwares. Our goal with EnsNano is to offer as many as possible of these functionalities in one centralized and responsive software that is easy to use and to install. Let me review in details the features of interest in every category. CADNano is one of the best-known DNA design softwares. The assumption made in CADNano is that the strands composing your design adopt the shape of rigid helices that can be considered and stacked like cylinders. And within that model, CADNano offers an abstract 2D representation of the design that makes the design process intuitive. The 2D interface of CADNano is very effective and is probably one of the reasons why today CADNano is still one of the most used softwares. The software Tiamat was released in the same year as CADNano and proposes a completely different approach. It offers a 3D editable interface that does not restrict the user to straight helices. The main benefit of providing a 3D interface is that it makes it much easier to work with the peculiar geometry of the DNA double helix. Without a 3D view, connecting strands from non-parallel helices can be very tricky. It should also be noted that Tiamat comes with a basic sequence generator and is therefore not limited to DNA origamis. Tiamat and CADNano are very complementary softwares. One of the main features of EnsNano is to combine a CADNano-like 2D interface with a 3D editable view of the design. There are several softwares that automatize certain parts of the design process. A recent example is Magic DNA that provides automatic scaffolding algorithms that can be used to quickly build large modular structures. Automation is obviously a desirable feature that improves the designer productivity. Note that designs always require some manual final adjustment. For example, Magic DNA exports the generated design to CADNano for manual fine-tuning. This is yet another proof of the fact that CADNano's interface is effective for design fine-tuning. DNA nanostructures are subject to complex geometric and physical constraints. In order to save money and time on experiments, designs are commonly checked with a physical simulation software before final order. OxDNA is one of those software, and here is a video of an OxDNA simulation from their YouTube channel. As you can see, OxDNA is able to perform fine-grained simulations of DNA nanostructures. These simulations require a lot of expertise and are a whole area of research by themselves. In EnsNano, we have a much more modest goal: provide a quick regular feedback to the viewer by implementing a simplistic rigid body engine similar to the one of OxDNA Viewer, the companion software of OxDNA. OxDNA Viewer has a rigid body engine intended to be used to guess the geometry of imported CADNano designs. In this example from the software public repository, the rigid body engine is capable of guessing the intended shape of the design by treating each set of helices as individual rigid objects. This kind of simulation is computationally much less expensive and can be integrated in design softwares for checking the structure local stability. Now, let me introduce you to EnsNano. EnsNano is a follow-up of CodeNano, a project that Pierre-Etienne Meunier and I started in 2019. It was program-based and not GUI-based, hence its name. EnsNano is a new project that uses the same data structure as CodeNano. Here is an overview of the features of EnsNano that I will demonstrate in a few minutes. The main feature of EnsNano is to provide a 2D CAD-Nano-like interface synchronized with a 3D view. EnsNano is focused on user experience. Many efforts have been put in the graphical interface to make them as intuitive and effective as possible. We also introduce original features, such as an iterative and geometry-aware copy and paste, a splittable 2D view, and a free organization of the 2D scene. Our model for representing design is almost the same as the one introduced in CAD-Nano. The strands in our design are supported by virtual helices that can be packed like cylinders. EnsNano has a 2D interface very similar to CAD-Nano's, with the additional capability of being able to freely move the helices around. Moving the helices in the 2D view does not affect their position in space, but allows to create a readable representation of the design. We also extend CAD-Nano's model by allowing multiple grids in the same design, so that the design can contain non-parallel helices. At the moment, EnsNano has three kinds of grids: 2 infinite lattices, the square and the honeycomb, and 1 finite circular grid for making nanotubes with up to 50 helices. As I have explained in the previous section, we have chosen to have both a 3D view and a 2D CAD-Nano-like interface. These interfaces are meant to work together and have been designed with a particular focus on user experience. Every routine operation is only one click away. For example, creating a strand can be done by clicking on a 2D helix and doing a drag and drop. Notice that the 3D view is synchronously updating as I am creating the strand, and that the 2D helix stretch. Deleting the strand can be done by selecting it and pressing delete. Dragging the extremity of a domain can elongate or shorten the strand. This can be done in 2D or in 3D. A simple click into 2D view can delete a crossover, and the crossover can be rebuilt by doing a drag and drop. Crossovers can be made like this in the 2D or in the 3D view. Note that crossovers can also be made from the inside of strands by doing a drag and drop. This can be done in the 2D or in the 3D view. A simple click can also cut a strand or merge two neighboring strands. I would now like to demonstrate how the 2D and 3D views work together to help you connect strands from different helices. This design was built to illustrate EnsNano's capability to handle non-parallel helices. This is a single DNA origami that consists of a rocket placed on top of a squared base. Notice that the helices of the rocket are not parallel to the helices of the base. Now, suppose that I want to connect this staple of the rocket to a staple of the base. Without crossover recommendation, it is not clear where in the base I could connect the staple. I will therefore enable crossover recommendations. To do so, I create two groups, one with the helices of the base and one with the helices of the rocket. Now, I will assign a color to each of these groups. Red for the rocket helices and green for the base helices. Assigning these colors enabled crossover recommendations. Now, when I zoom on the staple, I see nucleotide from helix 35 that can be connected to some nucleotide of an helix from the green group. Double right-clicking on one of those nucleotides, focus the 3D view on them. In the 3D view, I can create a crossover by following the recommendation. Now, by double-clicking on the crossover that I just made, I can split the 2D view and make the neighbor crossover. I can now play with the crossover in 2D and see how it affects the 3D representation. Notice that when the crossover becomes too long, it is displayed in black in the 3D view. So I can adjust the crossover in the 2D view until it seems correct in the 3D view. This demonstrates the effectiveness of the interaction between the 2D and the 3D interface. Let me now demonstrate a more elaborate feature of EnsNano, the iterative and geometry-aware copy and paste. Using this functionality, I will quickly build a SST nanotube from one single-stranded tile. First, I start by making a tile that connects helices 0 and 1. I will now copy this tile and paste it to connect helices 1 and 2. To do so, I select it and press Ctrl J. I place the copy with a shift of 8 nucleotides on helix 1. This copy operation has created a tile with the same structure as the original, that is, two domains of length 21. By pressing Ctrl J again, I can now create immediately a second copy. Notice that the transformation between the original and the first copy is the same as the transformation between the first copy and the second copy. This is how the iterative copy and paste functionality works, by applying the same translation and iterative copy within the grid and the helices. I can now create several tiles by simply pressing Ctrl J several times. I have now reached helix 7. If we only focus on the 2D view, we could think that it is not possible to copy the tile on that helix, since there is no helix 8. However, if we look at the structure in the 3D view, it is clear that a copy of this helix would actually connect helices 7 and 0, and indeed, this is what happened. The iterative copy and paste does not copy the 2D pattern, but rather the 3D geometrical pattern. I can now copy the strands that I have several times to build a longer nanotube. Finally, using the auto-roll feature, I can adjust the roll of the helices so that the crossovers have a reasonable size. Now, I would like to talk about EnsNano's physics engine. Here is a table that can help understanding the scope of our engine. Our goal is not to offer a precise thermodynamic simulations at all. I cannot stress this enough. Such simulations are outside our area of expertise and can probably only be handled by specialized softwares. They usually require a lot of time and are more likely to be used at the end of the design process to make a final assessment of the quality of the design. What we want to offer here is a tool that can be used regularly to provide a quick feedback on the design. For this purpose, we implement a rigid body model in which crossovers are modeled as springs. Our engine allows to test the stability directly in the 3D view and in a few seconds. Simulations that are run for more than a few seconds in our model are probably physically irrelevant. To illustrate the physics engine of EnsNano, I will use these origamis designed by Wu and Rothmund. The authors first made this first origami in order to study its stacking. The AFM images revealed that the origamis did indeed stack. However, the resulting chain appeared fragmented. The author's interpretation was that this apparent fragmentation was due to a twist in the origami. Then, they made a second design after adjusting their model of DNA. In the model used for this second design, the number of bases per turn of the double helix is 10.44. Using this model, they made origamis that stacked very well. They concluded that this model should be preferred for making DNA origamis. This led to the rule of thumb that in designs made in EnsNano, one basis should be deleted every 48 nucleotides. Let's compare the two versions of the design with EnsNano. This is the rectangle design without the nucleotide deletions. It should therefore not work well with EnsNano's model that has 10.44 bases per turn of an helix. Indeed, we first notice that the roll engine is not able to adjust all the helices to make all crossovers correct, and many of them are still colored in black. And now, if we try the rigid helices engine, we see that the design quickly collapses. This is now the version of the design where one nucleotide is deleted every 48 bases. First, we observe that the roll engine is capable of adjusting the helices so that all crossovers are good. And now, if we run the rigid helix engine, we see that this design passes the stability check of our engine. For a precise molecular simulation of their designs, user can export it to OxDNA. Regarding the file format of EnsNano, we use a JSON structure inherited from CodeNano and with several similarities to SCADNano's format. The parameters of the model of DNA are stored and editable in the file. So, if you want to work with a different value of the minor groove angle, for example, this is possible. At the moment, we can import SCADNano and SCADNano's design and export to OxDNA for thermodynamic simulations. The rocket design that I showed a few minutes ago was conceived entirely in EnsNano in a few hours. EnsNano is able to compute the sequences of the staple of a DNA origami with some optimization. Here are some AFM pictures that we obtained. As you can see, the origamis have the intended shape. The base and the rocket are both easily identifiable. This constitutes the first experimental success of EnsNano. To finish this presentation, let me tell you about the main directions for the future development of EnsNano. First, we will allow curved helices in EnsNano. Secondly, since our file format is compatible with scripting, we will provide soon a Python framework to generate designs. Currently, EnsNano does not offer many automation tools. The iterative copy and paste is some kind of way around this. We plan to provide auto-scaffolding and auto-stapling algorithms. However, general auto-scaffolding turned out to be more difficult than anticipated. Finally, we plan to provide a higher abstraction for the intended design to allow easier connection to sophisticated sequence designer programs, either external or internal to EnsNano. This will allow EnsNano to fully export non-origami DNA nanostructures. For that purpose, we may take inspiration from what was done in CodeNano. This concludes my presentation. I would like to thank all the other members of the molecular computing team at ENSW for their regular feedback on EnsNano. And I would like to thank all of you for your attention. I am now ready to answer any questions that you may have.